Okay, Bio 30, so far we've been dealing with monohybrid crosses whereby the genes only have two different alleles, a dominant form and a recessive form. But in reality, there are many genes that are controlled by multiple alleles. If you have a gene that's controlled by multiple alleles, so more than two different alleles, then you must know the hierarchy of dominance for those. So an example of that is present in fruit flies, where they have one gene that controls their eye color, but they actually have four different alleles for that eye color. So the hierarchy of dominance, looks like this. Simply that eye color allele 1 is the most dominant. It's better than 2, and 2 is better than 3, and 3 is better than 4. So this would be the least dominant. This would be the most dominant. Okay, and we're going to use that hierarchy of dominance to develop a key. Okay, so if we put E1, okay, in a genotype with another E1, or E1 with an E2, or E1 with an E3, or E1 with an E4, any of those genotypes would give us wild type eyes or red eyes in fruit flies. Okay, if we put an E2 with an E2, or with an E3, or with an E4, then we would get apricot colored eyes. Apricot, that is the debate. Potato, potato. Okay, we can't put an E2 with an E1 because that just gives us this genotype. E1 is more dominant, so then you'd get red eyes. Okay, to get honey colored eyes, you would put an E3 with itself, or with the most recessive allele, which is E4. And the only way to get white colored eyes, is to have E4 with E4. So anytime you see a fruit fly that has white colored eyes, you absolutely positively know its genotype. Okay. If you saw an apricot or apricot colored fruit fly, you would know that it has an E2 for sure, and then something else. You wouldn't know what the other one is. Unless you performed a cross, then maybe you could figure it out. I'll give you an example of that. So here's an example of using the offspring to figure out the parent's genotype. So if this was a cross right here, where we crossed an apricot-eyed fly with a honey-eyed fly, we would know that the cross would be E2 something, because that gives us apricot, crossed with an E3 something. And that's how I would write it. I would write it as, I know it has an E2, I know it has an E3, and then I don't know what its second allele can be. I know that it's, in this case, the second allele cannot be an E1. In this case, the second allele cannot be an E2 or an E1 because those are in the hierarchy of dominance would give it a different color. Okay, so this is either an E2, E2, an E2, E3, or an E2, E4. And with this one, it's either an E3, E3, or an E3, E4. And we're not sure, right? Just given the cross. However, if you're given some offspring in the question, for example, these fruit flies had several babies, and when the scientist looked at them, he noticed apricot, honey, and white-eyed babies. Then we can solve the unknown allele for those parents using a Punnett square and working backwards. Let me show you. So here's, there's our Punnett square. We're going to put what we know from each parent in here. So E2, here is E3. We're not sure what the other one is. But the key to solving this is right here. That white-eyed baby that they had, we know the only way to get white-eyed babies, because it's the most recessive allele, is to have that homozygous condition for that recessive allele. So that, if that's the case, I'm going to put one of those individuals right here in the bottom right corner, E4, E4. This is a possibility of a type of a baby that we can have. Perfect. So one of those alleles had to come from this parent. The other allele had to come from the other parent. We just solved the missing alleles for the parents. If we complete this cross and see, well, what else do we get? Well, we would get E2, E3. By combining those ones, we would get E2, E4. By combining those ones, we would get E3, E4 by combining those ones. Now, this does not say they had 4 babies and one was this and one was that and one was that. One was that. It does not say that. Remember, this is just a probability generator to tell me for every baby they have, what are the chances that it will be apricot? Or what are the chances that it will be honey? Or what are the chances that it will be white-eyed? Okay, so for their first baby, it has a 1 in 4 chance of having white eyes. It has a 2 in 4 chance, or 50% chance, of having apricot eyes. And it has a 1 in 4 chance of having honey eyes. What about the second baby? Same probability. What about the third, the fourth, the fifth, the 19th, 100th baby? What are the chances of it having white eyes? 1 out of 4. What's the chances of the 2 millionth baby having white eyes? 1 out of 4. What's the chance of the 18th baby having apricot eyes? 2 out of 4. Okay, just a probability generator. All right. Sometimes the question will give you they had 4 babies, 2 apricot, 1 honey, 1 white. A lot of times they give you that just to give you a clue as to what the parents are. Okay, but that's it's kind of tricky. Could I get 10 white-eyed babies in a row? Absolutely. I got a 1 in 4 chance every time of having a white-eyed baby. And that's just chance. Chances are, after I've had more than 10, if I had 20, 30, 40, 50 babies, I would probably see the numbers look more like a 2 to 1 to 1 ratio. So that's a little bit about probability in our multiple allele example of a monohybrid cross.